try to learn a little bit about solar photovoltaics, the fundamentals, how it works, and how to design them in this session. As Ms. Isha mentioned, kindly keep the questions towards the end of the session, and I'm most happy to answer as much as possible from my end. So let's start the session. So, ladies and gentlemen, here you can see a huge number. That's 3.8 yotta watts. That's the amount of irradiation coming from sun. But it's a good thing that not all of that energy is coming to Earth, else we'll not be alive. So a portion of that is coming to Earth, and basically the field of solar photovoltaics, it harvests that energy to produce electricity. So here is a famous quote from Elon Musk. You might be knowing him as a very prominent person in the field of innovation, and he owns a conglomerate. So he says that we have this handy fusion reactor in the sky. You don't have to do anything. It just works, shows up every day, and produces ridiculous amount of power. So now let's see how we can harvest this power and to generate electricity and make use of that electricity. So, ladies and gentlemen, I understood from Dr. Saif that the most of the attendees from the University of Taxila is final year graduates. Ladies and gentlemen, please take this as a friendly advice that please get the fundamentals right and enjoy the learning process. You can see the grounding doesn't work this way. I mean, if you do not have the in-depth knowledge of what you're doing, you tend to do a lot of mistakes, and that costs a lot of time and money for your organization. And also, on the same note, I'd say that it's on par with the fundamental knowledge that you should think safely, and you should think safety and you should work safely, because I mean, you're soon graduating as engineers, and you will build up your own team, and you'll be working in the capacity of a team leader, or probably you'll be working as a team member. You'll come across a lot of hazardous activities every day, and one wrong step can either cause a loss of life of your friend, your teammate, or yourself. So think safely, and make it as a habit that you always work safely. Thank you. So let's go through the topics. The topics would be the fundamentals of photovoltaics, various types of solar PV systems that we can see these days. We can see a little bit of theory of PV power and energy, how we can calculate that. I'll take you through the formulas, the design criteria, testing and commissioning of photovoltaic system, just a bit of it, because testing and commissioning itself is a huge field. Then scope for the engineers. I believe non-electrical engineering graduates may also join the session. So every walk of engineers or any specialty of engineers are welcome in this field. They have their own contributions, so I'll take you through them as well. So photovoltaics. Ladies and gentlemen, I would like to brush up your memory a little bit on the quantum physics that you probably studied in school or early in graduation days. So how is this radiation or the electromagnetic waves are generated? As you all know that the atom, the electrons in the atom, the physics lovers, we call them as saints. They don't like to move. They don't like to be touched or disturbed. So they all have their own energy band and their own chairs to sit in their respective atoms. And if something like an external force, they try to push these electrons for some reason, okay, then photons, it escapes from that atom. That's like, that's like a very loose translation I would like to give on certain principles of quantum physics. There are much more better mathematical or physical models available in the YouTube lectures that you can follow in future. But as we know that we have this huge fusion reactor who is very busy making helium up in the sky, and the sun is sending this electromagnetic radiation into Earth, right? Not just to Earth, it is scattered everywhere. All the planets received it. Not just planets, like even if you go out of the solar system, we can still see solar. Sorry, we can still see sun because the light energy is reaching till that point. So this light is nothing but an electromagnetic radiation. Okay, so a portion of that is the visible light, which we can see, but that isn't it. And thankfully, Earth has its own natural filters. Okay, the atmosphere itself is a filter, so it blocks away certain harmful radiations. Okay, gamma rays, X-rays, ultraviolet rays, those radiations that has a higher ionizing tendencies. Okay, so it gets blocked away, and also Earth has its own magnetic field that also helps in blocking these harmful radiation. Okay, now the visible light, along with trace amounts of other harmful radiation, also comes into the Earth's surface, the crust. Now, as this light hits a cell, a photovoltaic cell, you can see that it's just a p-n junction, but it's a special kind of p-n junction. You can see that here, you can see that a certain jumping of free electrons is happening, right? So these say we are giving these electrons a direction, and the push is from these light. So when this push happens, we get an electromotive force, right? So when we have this electromotive force, we get a DC voltage buildup. So this is the basics of how a photovoltaic cell works, right? But we have to configure this cell in such a way that we can make a solar panel out of it. I'll take you to that step. But before that, please, if you are really interested on how these things work, kindly read on the standard model of or of the about the fundamental particles of physics. It's called particle physics, and also about the electromagnetic spectrum and how all these waves behaves and from where it comes. It's an interesting read out there. Now, here is the anatomy of a solar panel. I'm sure most of you have seen solar panels. If it was a couple of decades ago, this was still an emerging technology, and it's heavily discussed. Now also, intense amount of discussion is going on, but we can see solar panels, thankfully, every day, and I'm so happy to see them everywhere. This is the anatomy of a solar panel, and the cells that you see, it is the central layer of the panel. So earlier, I explained these cells, right? How the cells works. Here, the cells are grouped. Some of them are put in series and some of them are put in parallel. It all depends on the manufacturer, how they would like to standardize it. And it has back encapsulation and top encapsulation because, you know, the cells are produced by cooking the quartzite, like the silicon, the silicon oxide, okay? To remove the oxygen, then they add a little bit of impurity called doping, and this cells are made into a wafer shape, and there are these electrical bus bars. These are the thin line that you can see that runs through the cell is called the bus bar that carries the energy, of course, and they seal this completely so that the oxygen will never ever touch these cells again, because the moment it is exposed to oxygen, all that effort on cooking these cells will go into vain, because it starts oxidizing there, it develops hotspots there, and it basically kills the function of that solar panel. So top and back, it's encapsulated, and again there will be a tempered glass on top of it to prevent damages from the external, like probably if there is a place that it hails a lot, so hailstones can hit, birds will sit, or if like where I'm from, we have a lot of dust wind, and there will be flying debris hitting into the modules. So it gives a little bit of mechanical protection, and also the tempered glass is a kind of high refractive glass, because it doesn't want to reflect a lot of light, because we are in the business of capturing light, so it ensures the best possible refraction, and everything is just sandwiched and tightened using an aluminum frame. These days, only aluminum. I've seen most say 99.99% it's made with aluminum because of its lightweight and improved mechanical strength. And in the bottom of the module, you will see a junction box. So that's where all these lines, these bus bars will get terminated. And you'll also see something called a bypass diode inside, because these modules will be put in series or in parallel. I will explain that in the forthcoming slides. Um, while they do that, if one panel is damaged or if it's bad, it should not kill that entire series. So that's why we have a bypass diode also inside a photovoltaic cell, sorry, a panel. And you can see different kind of installation of these panels on rooftop, on ground, tilted, flat. And here is a beautiful thing called a smart flower. I'll explain how it works. So and we have also installed in flexible photovoltaic panels. It's kind of a flexible sheet, a thin film sheet encapsulated in a polycarbonate material. It's flexible, and there is a field inside the PV industry called BIPV, which stands for Building Integrated Photovoltaic. Those who are very interested, like civil engineers who are very keen to harvest a lot of energy possible out of a luvers or on top of an atrium in a curved space, we can apply solar photovoltaics into that industry or that place as well. So here in these two places, you can see these are called static installations, which is the most conventional type of application. The modules are not moving, it is not tracking, it just faces the sky, that's it. And we will see that there are some places where you have a tilted installation also. I'll explain why there is a tilt requirement and the difference between tilt and flat. So if you're going for flat, you can have maximum install capacity, but the efficiency will be relatively less if you are farther away from the equator. But if you're going for a tilted installation, because if you're away from the equator, the tilt, the angle of that tilt gets increased. And if you're going for a tilted installation, then of course the adjacent rows can create a shade. So you have to put a gap in between these rows. So what happens is that you cannot achieve the same amount of install capacity as you do with the flat installation. However, the efficiency and the generation is more. So here is how a single axis system simply works. So a single axis system is a dynamic photovoltaic table. It will rotate on its horizontal axis by tracking the sun. However, we have another type of just a second, let me bring back the pointer. So here is how it looks like, a huge photovoltaic field with a lot of trackers. So as the sun goes from east to west, these tracker will also face east to west. And thankfully, we are very much indebted to the ancient astronomers who have really observed the sky well, and they have actually traced the path of sun. So be you are in the equatorial countries, in the Tropic of Cancer, Capricorn, or you are in the poles, you are nearby the poles, the astronomical knowledge is sufficient enough to actually predict the position of the sun on a given date at a given time. So we know this. So that is brought into a mathematical algorithm, and with the support of GPS, we can design the tilt ratios of the trackers. So we can know, or we know this day, that at what degree the table shall be tilted, or at what degree it shall be facing the sun at a given time on a given date. We also have a dual axis tracker. So earlier I showed you a photo of this beautiful flower shaped PV table. So it can raise up and down. Also, it can face east and west in these two directions. So this is why it is called dual axis tracker. This is a very simple application of a dual axis tracker, but there are more commercial models of dual axis trackers. But you will see this farther up towards the equator, mostly in Europe and Northern America. So you can see such kind of dual axis tracker. There are some photovoltaic plants in down there in the southern hemisphere, also in some in Papua New Guinea and New Zealand, and some in Australia as well, and of course in Latin American countries. So the need for tracking the sun is to optimize the amount of amount of energy harvesting. Like, it is just to optimize the efficiency. It is to ensure that the best possible sun energy or the light energy is captured for the power conversion. Okay, ladies and gentlemen, whenever you get time, please browse down one standard data sheet from any of the manufacturer that you come across for solar photovoltaic panels. You may see that the unit of its power is mentioned in WP. The P stands for peak, and there is a purpose. Like, if you rate a transformer, you can say kVA. If you rate a motor, you can say kW or a HP. But if it comes to photovoltaics, we always take this P along with us until we finalize with the DC side of the system. Why peak? Because you know that there are a couple of variables that actually affects the output of the module, right? So the first variable is the irradiation, means the amount of sunlight that is falling onto the module. The second thing is, what is the temperature of that cell? As we studied in probably high school physics, that H is equal to I square RT, which is a standard equation that we carry along, that the temperature is inversely proportional to the current, right? So more the temperature, lesser the current that conductor can carry. So these two are the prime variables. And also there is something called air mass also, of course, because there is an incident sun ray, which is, which is just coming through the atmosphere with certain densities, turbidities, masses, and different filters like ozone. So there is a standard physical model, we call it air mass, and the value should be 1.5. So when we talk about the power of module, we denote it with watt peak, which means if you get, say, a 500 watts of PV module, okay, the data sheet says that it is 500 watts or 450 or 455, whatever it is. It means that under standard testing conditions, and what are the testing conditions? It is, say, 95% of the manufacturer goes with this. It is 1000 watt per meter square of sun, which is exactly perpendicular. And the module temperature is kept at 25 degrees, and the air mass is 1.5. So if you test these panels in that condition, then you are going to get the results as follows. So we have, let's go through the characteristics, that you have an open circuit voltage, okay? And if you short circuit that, then this is the amperes that you're going to get. But we are not depending exclusively on this. We have something called maximum power point. We will discuss this we will discuss this very soon. So the power at maximum power point is 250 watt peak. So if you are purchasing a 500 watt peak or a 400 watt peak module, that means on standard testing conditions, it will give you the output of 250 or 500, whatever it is denoted in the standard testing conditions. Okay. Now coming to the maximum power point. This is very essential information in the field of photovoltaics. That you know that, okay, any voltage producing source, okay, once you start drawing the current, the voltage tend to go low, right? So more the voltage, more the current you can drive from it. And if it's a constant voltage, then once you start drawing the current, then the voltage tends to go low. Now, what is the voltage driving factor or the current driving factor here? It is just nothing but the amount of sunlight falling into a module. So please have a look at this graph. Here you can see that at 38 volts, it's giving 209 watts, right? which is coming from 38 times 5.5 amperes. But on the other end, to drive or to draw a lot of current from or more current from the panel, you can see that it will give you 7.8 amperes, but the voltage is very less. But it's a diminishing factor that the voltage will keep on dropping. So what happens is that if you draw a lot more current, then probably you will not get any good amount of stable power out of that module. So that's why there is an IV curve tracing mechanism, and also we call it the maximum power point, that without dropping the voltage, okay, if you're able to drive a constant current, that becomes the maximum power point. And a lot of inverters these days work in this principle. The next prime component is the solar strings. Ladies and gentlemen, if you're entering this business, please be aware that probably you're working in 1000 or 1500 volts DC with 9 or 10 amperage. It is more than enough to electrocute a person. A person can die almost immediately if you get such an electric shock from such cables. These cables are designed to carry high voltages. They are not of a high core size. They come maybe 4, 5, 6, 8 mm squares because it is designed only to carry like 9 amps or 10 amps, but the voltage is high. And these strings, which we call as the DC cables, it always comes in pair because there will be a negative pole and a positive pole. And why this string? Because sometimes, depending on the design requirement, okay, we either put the panels in series or we put panels in parallel. In either case, there is an interconnectivity required. And in some cases, there will be just one module itself. So in a commercial application, we try to put several panels into series to add up the voltage. Then we try to draw a certain amount of current depending on what's the irradiation at that time. Okay, so this is called solar string. And here you can see the kind of plugs that we use for interconnecting the panels. It's called MC4 or multi-contact 4. There are different kinds, different manufacturers. And this is the most common standard, which is MC4. If you disconnect it under load, it's going to give you a real health hazard because it can give you an arc flash. Ladies and gentlemen, I believe you have seen how a welding machine works, right? It works in the DC. And you can see that the moment that electrode is brought near a grounded metal conductor, you see how it creates an arc and melts the metal, right? So if you disconnect these connectors while it is under load or when the current is flowing through it, it is going to create such an arc. Now you can imagine the hazard behind it. Working of the string inverter, there are different kind of inverters used in the PV industry. I will walk you through each and every one of them. The first and foremost will be the string inverter. You can see that. Did I miss a different type of inverters? Just a second. No, we are getting there. Anyway, working of the string inverter. So the most commonly used commercialized solar power conversion device is string inverter. We say multi-string inverter also because that's more commercially viable. What you will see inside it is there will be some terminals for the DC cables to be plugged, and it will have a surge protection. Then there will be a circuit for the maximum power point tracking, and there will be an inversion circuit with IGBTs, of course. Then there will be a synchronization circuit because you are pumping in this converted energy into a grid, right? So the grid will be 240 over 415, or depending on different countries, the voltage will be different, the frequency will be different. So there is a sync circuit required, and there is a continuous monitoring and metering. So monitoring and metering is nothing but like you need to know what are the voltage between the poles. You need to know what is the respective voltage between a certain phase and its the neutral. And also you should know if there is any leak current happening, severe circuit issues, so that you have to monitor between the neutral and the ground also. In some commercial applications, in larger scale plants especially, this neutral is missing. It is not required. So we keep the plant in a floating status. Here is the internal circuitry of a standard a Grita inverter. You can see that there is a provision where the DC strings are plugged in. Then it requires a kill switch, of course, but usually we never switch this off while it is under load. As I explained, it can create a serious arc. And once this DC energy is coming into the inverter, it requires a surge protection, like in case of a lightning strike or a severe short circuit. It should protect the further circuitries within the inverter's motherboard. And there is a DC EMI filter. You know why an EMI filter is required, because of the interference. There will be multiple voltage levels and leakages. So it should not create any sort of harmonics issue. So there is a filter required in the DC side. Then once we get, say, a purer form of a DC wave, then these MPPTs will work. The MPPTs will try to find that maximum power point, and then it gives it to the DC bus. So all this power from the various strings will get sort of, unified at this common bus. And from the bus, the inversion circuits. I'm sure you all studied about the inversion circuits as a part of your academic needs, the IGBTs and how it works. So it converts the DC waves into sinusoidal waves. And at the AC, as you know that, I'm sure you must have done this in your labs, that you have seen the sine waves and oscilloscope, that you are not able to get like say 100% pure sine wave, right? There could be some phase-to-phase changes, and the waveforms will not match. There would be some DC component present, and so in this case, it requires an AC filters, and also it has an AC EMI filter also. So it tries to make the converted sine waves as pure sine wave as possible. That's it. Okay. But you can see that there is an AC relay also. Why do we need an AC relay? That, these inverters are not exclusively manufactured for one country, let's say. It is applicable for different countries. And the relays are also a protection device inside, because if the phase-to-phase voltage has an anomaly, if the phase to neutral or the neutral to ground or wherever it is monitoring, there is a problem, then these relay immediately desyncs the inverter and protects itself. And suppose if there is a high voltage in the AC side, then it cannot pump in the energy, right? So it again desynchronizes. So this is a protective device inside. And of course, as I explained, the EMI filters, it's like a correction device to give as much as possible pure sine wave as possible. And also the AC side have a surge protection device. The first photo that you see here is a central inverter. It is not a string inverter. I just added that photo because when you go to megawatt scales of application, then you need a central inverter. But for small residential applications, mostly people go for such kind of string inverters. And this is a 250 kilowatt string inverter you're seeing here. And as I explained earlier, these are the DC strings that is getting into the inverter that carries DC power, of course. It gets converted into AC and comes out of this big fat cable out here. And it goes to a transformer station. And now, see, this is the fundamental of photovoltaics. You have a DC power, you convert it into AC, then it's the standard grid that follows. I would not say completely standard, because the protection settings, the transmission is a little bit different, slightly different to the conventional power plants, because the transformers, the neutral, the start point is not Earth. We keep it floating for a particular reason. We have floating IT type of transformers in large scale string inverter based applications. Anyways, if you look into the data sheet of a typical inverter, whenever you get time, please browse for more and try to identify. You can see the details, okay? And there are a few key things that we as designers look into, that what is the maximum voltage range in MPP conditions? What is the maximum open circuit voltage range? So you can see here that it is like from 1000 volts. Sorry, it is maximum is 1000 volts, and the MPP voltage range is 320 to 800. So why the MPP range is lesser than the open circuit voltage? It's because once the panels are short circuited, it starts giving out current, and of course the voltage go less. But it should not go lesser than 320 because of the conversion circuit. It requires a certain threshold to work, and then it gives you like what is the maximum input current. So if say you have 10 modules, okay, then you put 5 and 5 in series, then you parallel it. Then what happens is that you have a sufficient voltage, but you are adding current also when you parallel. So if you have such an application when you need a higher current output, then you should never exceed these figures. If you exceed that, the inverter either will refuse to work, or you'll probably burn the internal circuit. And it will also give you how many MPP trackers are available, because see, if you go for say a 20 kilowatt or 30 kilowatt inverter, there will be multiple pots, but not all the pots has its own independent MPPs. It will have a reference string, so you have to look at the position in which that. So if A3 means, if you see A3 means the A has 3 pots, out of which the third pot has an MPPT. So that will be your reference connection. Then it just gives you more AC insights, like how much watts it can produce in volt amperes. The inverters can give you a certain amount of reactive power also, along with the active power, just to improve the quality of power to pump into larger distances. And according to the grid demand also, the larger scale photovoltaic plants can give like 300 megawatt or 400 megawatt reactive also, according to the grid needs. And it gives you the nominal voltage ratios under which it can perform well. And you can simply go through this. But the most important is that if you are going to design a PV system, I really believe that you will try to design something by yourself after the session. Please keep these information readily available, because you're going to need that while you do the simulations and configurations. So the type of photovoltaic systems, the largely used or commercialized used ones are called the grid tie systems. The beauty of grid tie system is that it is cleaner source of energy. It is highly bankable, which means you can make a lot of money from it, and it's easy to install, easy to operate, and easy to maintain. Also, during the peak hours, the grid, the other power plants in the grid can kind of take a break, or it can reduce its active power, so that you don't need to depend more on the spinning reserves. So, as you know that the conventional plants that we have, the fossil fuel based plants, accounts for the larger share of power production. So if it's a combined cycle, the natural gas, it every it kind of produces 0.18 kilogram per kilowatt hour. Okay, if it's a coal power plant, it's somewhere between 0.35 to 0.4. Sorry, if it's a coal power plant, it somewhere produces 0.3 to 0.4 kilogram of carbon per kilowatt hour. And if it's a diesel power plant, so if you look at a diesel generator, which is easily seen everywhere, it is kind of producing 0.8 kilogram to 0.9 kilogram, which is very close to a kilogram of carbon. So, ladies and gentlemen, I know that you all love driving. You have your own cars or bikes or whatever. You know that it gives you a certain mileage, right? Like if you pump in 1 liter of fuel, a carbon-based fuel, then you drive it for say 6 or 7 kilometers, which is the mileage of that vehicle. And it says that a liter of that fuel is burned, right? So when a liter of fossil fuel burns, it produces more than a kilogram of carbon based gases, carbon monoxide or dioxide. Why? Because burning is an oxidation process, so it bonds with the oxygen, right? And so that's the thumb rule. Every kilo of fuel that you burn, it produces more than a kilo of gases that is harmful to the earth. So that's why we in the renewable energy industry, we talk a lot about preserving this earth, conserving it by give it a good advantage of bankable financial models of renewable energy power plants and try to optimize the use of it. Now the grid-tie solar system then we'll go to, I missed, then the next one is standalone solar system. Standalone solar system is a very simple system that can cater to a dedicated load. Okay, the earlier one, the grid-tie system, it really depends on grid, which means it requires someone else to create the voltage, supply the voltage to that power plant, so that that power plant can inject the current into the grid. But in the standalone solar system, it is never grid connected directly. Okay, and it can cater to a dedicated load. Load here I mean that a certain wattage for a certain amount of time, because standalone systems it employs a battery for the energy storage. Okay, and we have hybrid solar system, which is a better version of the solar standalone system, that in case if the battery drains and it cannot give out any more power, or if there is an issue with the converter, okay, then what it does is that there is a bypass relay available, so that it can take the energy from the grid or a diesel generator and still ensuring that the power is going to the dedicated load of that system. We'll go through the circuitries and the block diagrams. The grid-tie solar system will give you a little bit of more insights. The grid-tie solar system employs grid-tie inverters, and there are micro inverters available. Like behind nowadays, the technology is very much advanced that the solar panel itself has an AC output, which means there is a micro inverter plugged into its junction box. And there is something called string inverters. These is mostly faded out. It's kind of getting obsolete. The most demanding inverter is the multi-string inverters, and there are central inverters. So the micro inverters are in few watts, okay, maybe up to 500 watts. But the string inverters from 500 watts to a few kilowatts, but it's kind of getting obsolete. But the multi-string inverters are coming from few kilowatts to few hundreds of kilowatt. There are up to 350. I believe it's the Sungrow, the manufacturer, who have pitched into the market with a 350 kilowatt of string inverter. And there is something called central inverters, which has its own transformer, it has its own monitoring and power transmission devices. These central inverters comes in multi-megawatt scale, 8, 9, 10, 20, etc. So the central inverters are used for large-scale application for a megawatt, power plant. We don't need that for our homes, of course. So here is the basic connection diagram of grid-tie solar system for a captive applications. So here I'm going to explain how the captive and independent power plant works. So what does captive means? That whatever energy you produce, okay, you're going to use it in your own loads, okay? So here you can see that there is a PV array. Then it is connected to an inverter. The direct wave gets into sinusoidal wave. Then you measure how much energy you're getting from the PV system, and you are simply pumping in that energy to a sub-distribution board. Even you can route it to the main distribution board. It doesn't matter, and it is absorbed by the loads. But the most important thing, the country in which you're going to design the PV system. First of all, you need to know the grid code, the grid policy. Why? Because in some countries, feeding power back into the grid is forbidden, and due to their limitations and restrictions, of course. So suppose if these loads are very less, okay, I designed such a system and the loads are very less. Say these inverters are producing 100 kilowatts, but my loads are only 80 kilowatts. So what happens is these loads will absorb that 80 kilowatts, and the remaining 20 kilowatts will go back into the grid. So in some countries, when we design the systems, we have something called a reverse feed protection relays and or soft reverse feed protection devices. So there would be another CTVT here with a monitoring box, and that box will tell this inverter that, hey, just limit your power or just go into shutdown. So please take a note of this. There is a reverse feed in protection. You can read further about such devices. There are relays and power limiters available in the market. Now, if you have say your country has a policy where you can consume PV power and also you can sell it to the grid. So in that case, a net metering model will come. That's not a captive power plant. That's a part captive power plant, because the excess energy, say the demand is 80, you're producing 100, then the remaining 20 you can pump in back to the grid. So what happens is that these kind of meters are the kind of meters, energy meters we use there is called bidirectional meters. It can rotate both ways. And billing, it's up to the policy. I cannot comment on that. It purely depends on the local grid policies. There is an independent power plant, which means, say, you have a house, okay, and due to some restriction, the grid people, they tell you that, okay, don't connect solar into your loads. Instead, you can sell it back to the grid, right? So you make a plant, you pump in all the energy into the grid, and also at the same time, you absorb that energy from the grid, and you exchange that bills, basically. Most likely the generation, the unit cost of generation is a little bit lesser than what you consume. That's how the grid operator in general they work. So an independent power plant, even if there is no dedicated load here, or forget about the house part. Okay, the MDB and SDB belongs to a house. It is not required. It is not necessary to be required. An independent power plant means you have lots of modules, you have lots of inverters, you do the conversion, you pump in that energy into the grid. So that's called the IPP, and I work for the IPP business these days. A standalone solar PV system. So, ladies and gentlemen, I'm sure you might be using a Casio generator which has a small solar panel in it, right? If not, please buy one. It itself is a small standalone solar PV system. It charges the battery, it uses that energy, and if the battery is dead, your equipment is dead. As simple as that. It consists of charge controller, a battery, and the battery comes from like few ampere hours to megawatt ampere hour scale storages are used in the market. There are systems that uses less than 200 watts, but if you really prorate a standalone solar system, you're actually making your own grid. It's called microgrids. I mean, these days there are several microgrid applications out there on top of mountains, on islands, on places where there is no grid availability. So you can actually make your own grid, and you can cater the power to villages, small towns, etc. from solar. So this is a typical single line diagram. I'm sure you're engineering graduates. Soon you're getting really into a lot of single line diagrams. You must keep a habit of drawing and improvising your skills in drawing single line diagrams. So here you can see that there are certain panels put in series. It is going through a fuse box as a level 1 protection. It goes to a charge controller. So this line is DC, and from there it goes to another battery inverter. In some cases, what happens is that the charge controller and battery inverter is formed together. Okay, you'll see just one device, but there is a charge controller and a battery inverter in it. In some cases, it's just two different components. So the charge controller is pumping in the energy into the battery. Now you see here we have 5 panels, right? And there are multiple of these 5 panel series coming into one charge controller, and there is just one output. So what happens is that probably this is like 800 volts, 500 volts, but the battery doesn't need that much of voltage because your battery bank voltage is just 48 or 24 or whatever it is. So when you're reducing the voltage of course, the amperage increases. So it's just thumb rule calculation. You know what is the input wattage from the circuit, then you know what is the output voltage from the circuit, then you can calculate what is the ampere that is getting into the battery. So I'll take you to the simulation side in coming slides to understand this concept better. And you can see that there is a common terminal here, right? What is a common terminal? The terminals that you're using to charge the batteries and to which the battery inverter is also connected. So if there is a daytime situation, there is a certain amount of load. So this mechanism will cater to the load also, and it will store the energy inside the battery also. So this is like a parallel operation. Please note, this is very important for you to understand whenever you design hybrid or standalone systems. You are sharing the energy to a load and for charging purpose. I'll come into detail in forthcoming slides. We sort of covered this topic. What is an MPPT charge controller? If you look at the charge controller's data sheet, these are the things that you're going to see, that what will be the rated current, what is the nominal PV power that you can connect into that particular model. You can browse down several websites of manufacturers to get these information. Working of a battery inverter is nothing but you have a battery string, which is a positive and negative cable coming into an overcurrent or over voltage protection circuit. It divides the input monitoring. So it does the input monitoring. Inversion circuit, it is making sinusoidal wave, a transformer, then it gives out that energy into the load. Simple mechanism. Hybrid solar system have one additional line, that it has an auxiliary feed, that if the battery is drained, then it will feed the power to the loads through an auxiliary input. That's it. Or it takes the power from an auxiliary input and yet it provides the energy to the load. This is like a typical installation, how it looks like with lots of batteries. So this is like a three-phase system. You can see that these big yellow boxes is a single phase battery inverter, and multiple of these makes RYB combinations, which is three-phase. And you can again combine these multiple RYBs using something like a multi-cluster box. I mean, it all depends on different manufacturers. They name it according to their wish. So what it does is that it makes RYB and also it combines the RYB. Off-grid inverters are used in such situations. We should take out the grid type part. There are various types of cells used. Cells in terms of energy storage. The batteries used in this standalone and hybrid application. It's like nickel-based, which is nickel cadmium, lead-based, such as flooded, VRLA, AGM, gel batteries, lithium-based batteries. Your mobile phone has a lithium-based battery, lithium, nickel, manganese, cobalt oxide, which is like LiFePO batteries. Then there is redox floor batteries. You can browse and read about these further about these kind of battery. Each has its own advantages and disadvantages. Its own intrinsic characteristics, IP ratings. So it's a huge world out there. A good electrical engineer can always excel in the field of battery storage. And there is a term called battery energy storage systems, which is a very promising field of engineering these days. Let's go to the designing of a solar photovoltaic system. So this is the most important thing, that you should understand what is a customer's load profile. I'll show you the samples of that. What is the available space on the roof? What are the customers' need? Product and technology availability, design viability, budget factors. Maybe somebody has money for only 1 kilowatt system, but they ask for 2 kilowatts. Of course, you cannot deliver that system. So budget factor also pitch in. Then maintenance factors. Don't put modules and inverters in a location where you cannot access it for maintenance. It's of no use. Then you can make use of simulation tools. There are performance of a system, can be much more accurately be assessed using simulation tools. You can ensure that the compatibility is verified. Like some inverters cannot take this much of capacity. So simulation software does this job for you, whether you are in the safe working limit or not. And it uses a calendar year's weather data to simulate the entire system, gives you, okay, in February, you're going to get this much energy. In March, you're going to get this much of energy, etc. Here I've given some names of simulation softwares. I'll definitely share these slides after the session. Before we go into the simulation, you have to understand what is the DC power and how to calculate the DC power. So this is the formula for that. So you have a PSTC, which means the power at standard testing conditions, which is the number of modules times the rated watt peak of the module and the number of streams. Okay, and there is irradiation factor. Here I've mentioned POA, which means plane of array, in case if you're designing a tracker system. But if not, if you're going for a plane system, then we term it as GHI, which is global horizontal irradiation. Simply means what is the amount of sunlight falling on top of a flat module, a non-moving module. Okay. Then there is a temperature factor, which means there is a coefficient of temperature for every module. You will find that information on the corresponding data sheet. Then you run through this equation. It's very linear. You can get the factor. And once you multiply the factor and divide by 1,000, then you will get what is the PDC in kilowatts. Okay. Energy calculation. You have an so you calculated the DC, right? You calculated the DC power, but you need to know what is the AC power. Very simple. You simply browse the data sheet of one string inverter or the inverter that you're going to use. It will show you what is the maximum efficiency. So if you get, say, 100 kilowatt of DC power, then times 0.98 will give you the AC power. This is the equation for energy. Look, in the PV industry, we always discuss energy. That's our thumb rule. That's the key factor that we all work in. We need to know what is the energy that a system is going to create or it is going to generate, either for selling purpose or for storage and load consumption purpose. This is the equation. I'll share you the slide. I really request the students to make a simple Excel sheet using this equation. It would be a very good activity for you. Ladies and gentlemen, you're all electrical engineers. Please go back to your home. Try to make a load profile of your home. If you are awake 24 hours, of course, or you can at least try to make for half a day, for 12 hours, whenever you have time. The load profile information is very important. Why? If you're going to make a system, be it grid tie or be it standalone system, the load profile is a key information that shows how the energy is getting distributed or the distributed energy consumption with respect to time. Say here, you can see that the hourly profile from, say, 7 o'clock to say 11 o'clock, the consumption of your home, that person's home, was very high. Then thereafter till 3 p.m. it's very minimal. After 3 p.m. again, it's getting high. You see, so this is the daytime load, right? When the sun is really shining. So if you underrate the solar panel catch area or the number of modules, what will happen is that it will not have enough energy to cater to the load and to charge the batteries for nighttime use at the same time, right? So when you design such systems, you always have to have a look at what is the amount of energy consumed during daytime, which means when the sun is shining, and during the nighttime. You have to find a perfect balance. Let me discuss with your professors. If there is time available in a future session, I can help you with actual designing, because it's a very lengthy subject. Now I'll just go through the basics. So see, there is a space availability on the roof, which should not have any shades. You can see the sun, it is going in a direction that the panels are facing the sun. From the PVSys software, you get something like an insolation report. You can read this further. It shows you at what time and at what azimuth the sun is there and what is the amount of light. Ladies and gentlemen, going back to the fundamental physics that we learned during school time, the winter solstice and the summer solstice, which means the lengthiest day and the shortest day. And also we have equinoxes, which means the day length is equal, right? Sorry, the day to night hours are equal. It's all because the sun, the earth has got a tilt and it is rotating around the sun. So this is an important information that we have to design the system properly, because say we are going to design a standalone system, it should work throughout the night on a winter solstice, right? Which means we get very less hours of daytime energy to store the energy that is required for the nighttime operation. So we calculate that. Please visit suncalc.org. It's absolutely free, and I believe I tried to pinpoint your university to the best of capacities. Please accept my apologies. I don't read Urdu. Unfortunately, it was giving only Urdu. You can go to your home basically in this website and see how the sun is going above you in different dates. So here I've taken on 21st of December. You can see that the sun is farther out, and on this line belongs to the 21st July, which is the time when the sun gets on the maximum apex top in your location. So during winter the sun goes farther away, and during the summer days it comes farther up. So please use this tool. It's absolutely free. And there is another tool freely available in the internet for very basic calculation. It's called PVGIS. You can make a simple system in this and try to simulate it, and it will give you this value. So here I just simulated 1 kilowatt peak of solar system with an estimated 10% of efficiency loss. Then see how the values are coming up. I believe I pinned that position properly into the town that you're attending this webinar from. You can see that in January it is giving this much of energy, and from Jan to December on different months, different amount of energies. This is a key information that you need to know while you design a standalone system or a grid tie system. I'll try to skip this because we are really exceeding the time limit. I'm really sorry, the organizers. See, a simulation report will give you a much insight of how you configure the system in a simulation software. What are the nuances that comes out after simulating it? Then it gives you an energy loss diagram. So I'll quickly take you through this. Look, here you have 2,283 kilowatt hour per meter square available, okay, because you have such a big catchment area. But there are several losses happening due to module mismatch, quantity losses. The STC value, while you verse that against with STC, what are the conversion losses? Like you are converting DC to AC, you're storing so much, and you're even directly using so much of energy, and there is this is the total energy that you're getting out of that system. And if you see a missing energy, see this missing energy part only comes for a standalone system. So you can try to download a student version. There is no student version. There is a demo version of PVSys available. You can please try to configure using some weather data. I'm sure it will not give you the data for your own town, or your own country, but it will give you something else. But that's enough to study the basics. Ladies and gentlemen, there are some mistakes when it comes to PV system design. See, a perfect system is always engineered, okay? If you see a solar system in your friend's house, if you try to copy paste that system into your own house, maybe it will not work, because as I said, there is a load profile. Every person is unique, same way every house is unique. So you need to understand what is the load profile of your home. Then you have to go through several factors that you should not undersize the system. There should be shade analysis done, that at what time of the day a tree is causing a shade on top of your module. That information is very important. The orientation and the tilt. This PVGIS can give you what is the best tilt in your location and what is the azimuth. Azimuth 0 means true south and 1 means towards west. So you can read through these definitions. I'm just introducing you these things, okay? You can further explore this. You have to calculate the ampacity. I'm sure you're all qualified engineers to calculate the ampacity of a cable, the wrong selection of cable. And please remember, DC cables and AC cables are two different type of cables in terms of construction. It's so you should not use AC twisted pair cables that you find in the market for a DC application. You can create a fire hazard or underperformance. Either you oversize or undersize the battery, you're not going to get a proper result from that system. So, these are the common mistakes. And I've seen this issue with a lot of electricians I've come across, that they always try to copy paste the systems, and customers are really unhappy. So load profile, that's the key. Please bear that in the mind. Testing and commissioning of a system. Ladies and gentlemen, I'm sure by the time you reach the final year of your graduation, you have come across this term called efficiency a lot. It's just a comparison between input and output. So what is the input and output of a PV system? First, input, you can calculate the input. I took you through the equations to calculate what is the theoretical input of a PV system, right? You calculate the power DC, then you can calculate the energy, right? Then you can measure the energy on the output. Once you compare this, then you know what is the performance of your system, how much amount of, so at what percentage your system is functioning. Ideally, in a well-maintained, well-balanced, a good product can give you a positive tolerance, because these modules, even if it says that it is 200 watts, it gives you a little bit above, say 5% excess energy. It need not to be the case with all the manufacturers, though. There are some requirements for pre-testing and startup. A bad move can cause a hazard. This is an actual photo that happened in Middle East. You can see how the string fires, damage the modules. The testing and commissioning team will first conduct a thorough site walk to identify any defective parts, any discrepancies, if there is any non-conformance to any sort of engineering documents that they have. They make 100% corrections. Then the strings carries like 800 to 1000 volts for a small scale application. For the plant where I'm working, it is 1500 volts. They take extra precaution during plugging in activities, because it's a high energy field you're plugging into an inverter. The battery bank may be in megawatt hour range of storages. Extra precaution is taken care. They do an internal check. They make sure there is no dust. These fuses are plugged in only in the last moment because they don't want to leave any conductor unnecessarily energized. They clean the module. It is very important to clean the module, because you're going to test a system. So that system must be ready to receive the maximum possible energy. They do the preliminary checkup. Ladies and gentlemen from the college, students, please try to buy one of these simple things according to your budget that you get from home. It's not very expensive. Maybe you can form a group and try to buy. It's called a multimeter with a clamp in it. So it's a multimeter with a clamp meter. This is very important, because if you're trying to understand the load characteristics of any device that you're working with, this is very important. This is very not so expensive for a small home kind of application. I believe it comes in, say, less than $100. This in the PV system, we check the voltages. If the voltages are fine, we compare with the different strings. Say if you have 10 strings and I'm getting almost similar voltage for 9 strings, and one is giving me, say, 70% less, that means there is something wrong in that string. So we can go and check that string before we plug it into the inverter. We also do something called IV curve. It's a huge topic. Please read to it. After plugging in the inverter, we observe the startup and the process in which the inverter wakes from the sleep. During that process, it checks the different voltage levels at the terminals, and then it is kind of ready to convert that energy into AC. It gives you a signal, okay, I'm ready to pump an AC. So then we switch on the AC also. Once it is done, the inversion starts and we take the reading on both sides, what is available from the DC, what is available from the AC side. These are some reports that we check, like what is the irradiation from the sensor. Here is an pyranometer. Here we can see a pyranometer and a module temperature sensor. And using this information, this is the Excel sheet I requested you to make using this equation. I've given this equation already. So what we do is we just copy paste the different irradiation readings taken for about 4 or 5 hours and the corresponding module temperatures. And the ambient temperature and wind speed doesn't really matter. It is not required for the equation, it's just for comparison's sake. Availability should be 100% if the inverter did not trip for a certain period of time in between. However, you can calculate the energy target here. So this is the energy target, okay? And this is the energy measured. This is why I said that if it's a good quality of PV module, then it will give you a little bit of extra energy for that amount of operation. But if, see, the target is 706 and you're getting only 520, 530, something like that, that means there is something severely wrong in the system. Either it could be equipment underperformance, or there is some shades on the module, or there is a defect in the module itself. So the testing and commissioning team can go back and trace into the defects. Okay, then they can take corrective actions. Okay, we are entering the last portion of our class. Scope for engineers. Ladies and gentlemen, please note that the combined annual growth rate of solar industry till 2020 was very promising. Of course, the COVID situation, the pandemic situation slowed down the market. Yet during the COVID, approximately 4 or 5 gigawatt of power plant has been already built across the world, out of which 800 was the plant in which I worked. And this is a very promising field, as several countries or association of countries are really pitching in a lot of money into renewables. They're all thinking greener these days. And as I told you, a solar power plant in a huge scale in a country, it's giving a lot of break to the conventional power plant that they have. So daytime they can really depend on the solar power plant to take as much as possible energy. Also, there are so many policies in the world, in different countries in the world, that the government give you subsidized installations, so that there are so much space which is wasted in terms of rooftops. Unless it, you can make such rooftops into small photovoltaic plants that will help in reducing the loads drawn from the power plants, thereby reducing the carbon emissions. So this is from the Wood McKinsey magazine. There are so many agencies in the world like Goldman Sachs and the Times. They all do this analysis, the kind of forecast in the market. You can browse through them, but I can assure you that the field of renewables is a very promising field. This shows the shares of the growth in terms of solar PV, hydropower, wind, and biopower, geothermal, ocean power, and concentrated solar power. There are opportunities for almost all types of engineers in the field of photovoltaics. So we need civil engineers and mechanical engineers for the drilling, for the piling, for the trackers, the production of silicon itself. We need electrical and electronic engineers for the PV panel, production, project management, construction, testing and commissioning, etc. We need data sciences engineers like IT specialists, and computer science for making the SCADA software, for the control softwares, for making the firmwares of the inverters. It's a soft system. We need, numerous R&D positions are available across the globe. Once you are done with your masters in this field, you can enter the R&D. several OEMs, the original equipment manufacturers of PV modules, inverters, they all need good researchers so that they can pitch they can contribute their product into a fast evolving market. Ladies and gentlemen, thank you so much for patiently bearing with me through this session. If there is any questions, we can proceed to the same. Also, please note that I've given my email ID below. I'm sure if the time exceeded for some reason, you can always ask me question, and please remember to copy the question to your corresponding academic person, the tutor or the event coordinator, just to keep a track of the answers I give, so that I don't need to repeat the questions. Please make a group and ask that question in that group, so that when I answer, it reaches to everyone. Thank you so much once again for patiently hearing me. Let's proceed to the question and answer sessions.
Thank you so much, sir, for plenty of information. Now move towards the question and answer session. If any of you guys have a question, you can ask.
I can hear a big silence from the other side. Okay. Was the class informative to all? Did you get at least a small pinch of information that I shared here? Can anyone confirm in the chat room, please? Was it informative? Because there are more than 40 persons in the group, and I'm so surprised to see that there are no questions. This is the first time I'm encountering such an situation. I think it's already late in Pakistan, where most of the attendees are from. It's all right. If there are no questions, it's fine. You can always write to me in the email. Please, if you're a student, please make a group and ensure that you copy that question to your academic representative, the tutor or professor as well. And I'll be honoring that request to answer that question. I will share the slide.
It was so informative session. Thank you so much, sir. It was so informative session, sir.
Thank you. You're welcome, Mohammed. So shall we wind up? I believe there are no further questions. You're welcome. Thank you once again.
Thank you so much, sir.
You're welcome. Thank you, ladies and gentlemen. Thank you. Wish you a good day ahead. Bye-bye. Good night. Thank you.
Thank you so much, sir. Allah Hafiz.
Guys, kindly leave the meeting.